Chapter 3 of our text starts us on inference. Inference is all about using a statistic from a population, or from a sample rather, to learn about a population parameter. So from a sample proportion, we want to learn about a population proportion. Or we want to take a mean of some quantitative data, and from the sample mean, x bar, we want to learn about the population mean, mu. And as section 3.1 and 3.2 of our book make clear, the key to all of this is going to be the sampling distribution. The sampling distribution is the collection of all sample statistics for a given sample size. And we're interested in what can happen. What does that look like? The collection of all sample statistics for a given sample size. What are the possibilities? What's the shape? And how much variation is there in those sample statistics? And that variation in the sample statistics is called the standard error. It's the standard deviation of the sampling distribution. It's the average amount by which a sample statistic differs from the population parameter. So that's a lot to take in. Let's see how Statkey can help us understand it. So we're going to go to Statkey, and let's just start from the beginning, and go to sampling distribution. We'll start with proportion. And I'm going to make the proportion 0.5. So we should imagine here looking at a election, a political campaign where the race is tied. 50% want one candidate and 50% want the other candidate. And let's choose samples of size 100. So suppose you went out into a population where the true population proportion was 50%. So 50% voting for candidate A, or 50% of the actual population are women, or whatever. So we're assuming that the population proportion P is equal to 0.5. Now we're going to look at a sample of 100 from that population. So let's just generate one sample. So you go out and you sample, you survey 100 people, and maybe you don't find exactly 50%, maybe you find 51%. Or do it again, it's also 51%. Do it again. This time it was all the way down here at, looks like about 44%, or 0.44. And let's just generate a whole bunch of samples at once. There's 100, there's another 100. So each dot here represents the proportion out of 100 people who are in our category, voting for candidate A, or one proportion who are women, or whatever it is we're proportioning, whatever we're interested in the proportion of. So notice there's quite a bit of variation. If in a political campaign, if the race is actually tied, it's actually a tied race and 50% want your candidate and 50% want the other candidate, if you go out and sample 100 people, well, we got one example that was as low as 37%, and one example that was as high as 63%. When you move your cursor over the dots, it tells you the proportion there. Okay, and the standard error is 0.05. So that says that your sample proportions typically vary from the actual population proportion of 0.5, typically vary from that by about 0.05. Pretty widespread. Now let's see what happens. So let's just be clear. Each one of these dots is one p hat. The actual p is 0.5, but each one of these dots represents one p hat, one sample proportion. And this picture shows us how spread out the sample proportions could be and what kind of variability there is. And the variability is 0.05. Now let's suppose that we change the sample size to 400. So now it's as if we're going out and every time we generate a sample, we're surveying 400 people and asking them who they're going to vote for. So our first one came in at 0.485 and our second one came in at 0.504. And if we generate several hundred samples, well, once again, they're centered at around 0.5. Notice that now the standard error is only 0.025. So with a larger sample size, the amount of variability in the sample statistics is less. In both cases, you get numbers, you get sample proportions that are above 50% and below 50%, but there's not as much variability when you have a large sample size, and that should make a lot of sense. Look what happens when you really kick up the sample size to like 1600. And let's generate a couple hundred samples. Now the standard error is only about 0.013. So if you're looking at samples of size 1600, you expect the number you get to not vary, not be too different from the actual population parameter. So the way we do this in Statkey is we come to Statkey, sampling distribution for proportion, put in whatever proportion you're interested in, put in whatever sample size you're interested in, and then just generate a bunch of samples. So as a check your understanding, you try it when the population proportion is 0.9 instead of 0.1, and try it for different sample sizes from 100 to a couple thousand. Now what if we're talking about means instead? What happens to sample means? Well, let's look at our Dane County homes data, and let's just look what happens when we look at the whole data set. So that's Dane County all at once. Now, by the way, Statkey does not like dollar signs and it does not like commas in its numbers. So whenever you're dealing with large numbers that have commas, or whenever you're dealing with dollar signs, once you select your column, before you try plugging it into Statkey, go up here and click on General, and notice that that took away our dollar signs and our commas. Now I'm ready to grab column B, and I'm going to put it in Statkey, sampling distribution of the mean. And so I edit the data, get rid of everything that's in there, paste mine on top of it. I don't have a first column this time, so I get rid of that. I do have a header row. It says price, so these are the prices of like 3,000 houses in Dane County. Hit OK. And notice that it tells me about the original data set, the whole data set. There's 3,125 houses. The mean is $319,000. The standard deviation is $288,000, or $288,292. So there's a huge amount of variation in the prices, which is not surprising because we know that there's some really expensive houses. Now let's look at samples of size, let's say 25, and generate a couple hundred of those, several hundred samples of size 25. Notice that the average of our sample means, so each one of these dots represents 25 houses taken from our original data set, and it gives the average, the mean for those 25 houses. The average of all those sample means is 316,000, which is not that far from the 319,000 for the original population. The standard error is huge. It's 52,270. So these sample means vary all over the place. Here's a sample mean of 25 houses, which is $531,000. Here's a mean of 25 houses down here on the far left, which is only 229,000. Lots of variation. Lots of variation. And even with a sample size of 25, this looks a little skewed. Okay, this does not look like that symmetric bell-shaped curve. And partly that's because our sample sizes here are pretty small, 25. Each dot represents the average price of 25 houses from that original population, the original data set. Look what happens when we look at a different sample size. Let's just kick it all the way up to samples of size 400. And now let's generate several hundred samples. So now each one of these is the average of 400 homes. So there's still variability. Well, first of all, the average of all these sample means is real close to the mean of the actual population, the mean of the original data set, 319,308, 319,791 for our sample means. So it's centered pretty closely to the mean of the original data set. But the important thing to notice here is the standard error now is only $13,000. It went way down, well, 14,000, but it went way down, So it was like, what was it, 288,000 before, and now it's only about 14,000. So this tells us that when we have larger sample sizes, unsurprisingly, the sample means that you get don't vary as much as when you have small sample sizes. In other words, the average price of 400 randomly chosen houses is likely to be closer to the true population average than if you just looked at 25 random houses, and that ought to make sense. So as a suggestion to see if you get this, see if you can do something similar for the data set consisting of the weight of all the people in our health or our health 2 data, and look at, put in the original data and then look at different sample sizes. So small sample sizes, larger, really large. Just get some practice with that. And again, the standard error here of about $14,000 tells us that these individual sample means, so this start is the average of 400 houses, the average price of 400 houses, and so is this start, that this standard error of about $14,000 tells us that these individual sample means differ from the mean of the whole population, the thing we're actually interested in, the 319,000, differ from that by on average just under $14,000. So again, to do this in Statkey, just put in the data, edit the data, put in the data, choose your sample size, and you're all set to go. So if you can get some practice with this, that will make things go more smoothly in class. I hope this is useful.